The machine does not start gently. It begins with a low vibration that you feel before you hear. A deep metallic hum travels through the concrete floor, up your legs, into your chest. Then the spindle begins to rotate, slowly at first. A steel cylinder, nearly 4 meters in diameter, weighing over 120 tons, turns on its axis. The chuck grips it like a clenched fist. Coolant sprays in a constant stream. The air smells like hot metal and oil. Then the cutting tool moves in, a single-point tool. Carbide tip, advancing at just a few millimeters per revolution. And yet, as it touches the surface, the sound changes instantly. A sharp, tearing resonance. A continuous scream of steel being shaped, not cut, shaped. Layer by layer, a ribbon of metal peels away, glowing slightly from heat, falling in long spirals to the floor. Inside some of these machines, the cutting force can exceed 20,000 newtons. The spindle torque is enough to rotate objects that would crush a truck, and yet the movement is precise, controlled down to fractions of a millimeter. This is the giant lathe, a machine built not to create small parts, but to shape the largest pieces of industrial civilization: ship propeller shafts, turbine rotors, pressure vessel components, massive steel rings used in energy systems, objects so large that they cannot be moved easily. So instead, the machine is built around them. For decades, this machine has been presented as something almost inevitable, a natural step in human progress. As industries grew larger, machines grew larger. As demand increased, precision followed. That is the story most people hear. In textbooks, the development of large-scale machining appears as a clean evolution. From hand tools to early lathes to steam-powered machines to electrically driven precision systems. Each step framed as improvement. More power, more accuracy, more productivity. In museums, giant lathes are often displayed as symbols of engineering triumph. Polished surfaces, cutaway diagrams, clean lighting. The narrative is clear. These machines allowed humanity to build ships, power plants, and infrastructure at unprecedented scale. They made modern life possible, and in many ways, that is true. Without machines capable of machining 100-ton steel components, entire sectors of modern industry would not exist. Energy production would stall. Transportation would shrink. Heavy engineering would slow dramatically. So the story becomes simple. Bigger machines leads to greater capability, leads to societal advancement. A straight line, a logical progression, a success story. Even the environment in which these machines operate is often simplified. Factory floors are shown as organized systems, engineers monitoring processes, operators controlling interfaces. Everything appears coordinated, predictable, under control. But if you look closer at the actual conditions these machines operate in, the picture becomes less clean, because a machine capable of holding a 100-ton workpiece is not just large. It reshapes the entire environment around it. The foundation beneath it must absorb constant vibration. The temperature of the workshop can affect tolerances by measurable margins. A difference of just a few degrees can change the dimensions of a component by fractions of a millimeter. And when tolerances are that tight, those fractions matter. The operator does not simply run the machine. They monitor sound, tool wear, heat distribution, material behavior. A slight deviation in cutting tone can indicate a problem forming deep inside the metal. And when something goes wrong, it does not happen gently. A tool can shatter. A workpiece can shift. At these scales, even minor instability carries enormous force. Yet these details rarely appear in the standard narrative. Instead, what remains is the simplified version: a powerful machine, a skilled operator, a controlled process, progress made visible, and easy to understand. But if this machine truly represents progress, if it is as central and as well understood as the story suggests, then a question begins to emerge, quietly, almost unnoticeable at first. Why do the descriptions of these machines feel so clean, when the physical reality around them is anything but? And why do certain details about how they were used, where they were placed, and what conditions surrounded them appear so rarely in the version of history most people are taught? At first, the records seemed to confirm the familiar story. Production increased. That part is clear. By the early 20th century, giant lathes were already machining components that would have been impossible just decades earlier. Steel shafts over 20 meters long, rotors weighing more than 80, sometimes 150 tons. Surface tolerances measured in hundredths of a millimeter. Factories reported higher output, shorter machining times, greater uniformity. On paper, this is exactly what progress is supposed to look like. But when you read deeper into technical reports and workshop logs, another pattern begins to appear. Not dominant, not always emphasized, but persistent. For example, in several early heavy machining facilities, engineers noted that as workpiece mass increased, so did instability. Not dramatically at first, just small observations, vibration patterns that were difficult to predict, tool chatter that appeared unexpectedly, even under controlled feed rates, surface imperfections that required repeated passes. In some cases, a single machining operation could take dozens of hours, only to be restarted because of a deviation that appeared near the end, which raises a quiet question. If precision was improving, why did rework remain so common? Another detail appears in maintenance records. Cutting tools did not simply wear down gradually. They sometimes failed suddenly. Under high load, carbide tips could fracture without warning. Fragments would scatter at high speed. In enclosed machines, this was contained. But in earlier open configurations, the environment was far less predictable. Operators stood within meters of rotating components. A 100-ton workpiece spinning at even low RPM still carries enormous kinetic energy. And yet, documentation from the period often describes these setups in neutral, almost procedural language. Operator positioned adjacent to tool post. Manual adjustment of feed observed. Interruption due to tool failure. The tone remains technical, measured, but the physical reality implied by these descriptions feels more intense than the language suggests. There is also the matter of temperature. Large-scale machining generates heat unevenly, not just at the cutting edge, but across the entire mass of the workpiece. A steel cylinder of that size does not heat or cool uniformly. Internal stresses shift. Dimensions change slightly as machining progresses. Some engineers noted that a component could expand enough during cutting to affect final tolerances, only to contract again once cooled, which meant precision was not just about measurement. It was about timing, about predicting how metal would behave under heat, pressure, and time. And yet, this level of complexity rarely appears in simplified accounts of industrial machining. Instead, the process is often described as controlled and repeatable. But in practice, it seems to have required constant interpretation. Another detail appears when looking at factory layouts. Giant lathes were not just placed into existing workshops. Entire buildings were designed around them. Reinforced foundations, deep concrete bases to absorb vibration, overhead cranes capable of lifting 200 tons or more. The machine dictated the structure, not the other way around. Which raises another question. If these machines were simply tools, why did entire facilities reorganize themselves around their presence? And then there is the human factor. Increased production did not necessarily mean reduced human involvement. In many cases, it meant a different kind of involvement. Operators needed to understand not just controls, but sound, rhythm, subtle changes in vibration. Some accounts describe experienced machinists detecting problems before instruments could. By ear, by feel, standing near machines producing continuous noise levels well above 90 decibels. For hours, sometimes entire shifts. Ear protection was not always standard in earlier periods, which introduces a tension in the narrative. Machines increased capability, but they also introduced new kinds of exposure. Not always dramatic, not always immediate, but cumulative. And then there are accident reports. They are not always easy to find, not prominently displayed, but they exist. A misaligned workpiece, a failed clamp, a sudden shift in rotation. Events that, at this scale, carry consequences far beyond what smaller machines would produce. And yet, these incidents rarely appear in the broader story of industrial progress. Instead, they remain in technical archives, separated from the narrative that most people encounter So a pattern begins to form, not a contradiction, but a misalignment. On one side, a clean linear story. Larger machines lead to greater precision, lead to improved industry. On the other, a more complex set of details. Unpredictable vibration, thermal distortion, tool failure, environmental dependency, continuous human interpretation. Both are real, both are documented, but they are not presented with equal weight. And that leads to a subtle but important question. Why do these more complicated aspects, the ones that describe uncertainty, instability, and risk, appear so frequently in technical documents, but so rarely in the versions of history that are repeated in textbooks, museums, and general narratives? If you place the popular narrative next to the technical record, they do not contradict each other, but they do not align cleanly either. In the popular version, the giant lathe is a symbol of mastery, human control over material, precision applied at scale, a machine that transforms raw steel into exact geometry. The emphasis is on outcome, finished components, perfect tolerances, smooth surfaces. The process itself is compressed into something almost effortless. But in technical manuals, workshop notes, and engineering journals, the process looks very different. Not effortless, not even consistently predictable. For example, in machining theory, stability is not guaranteed. Even today, chatter vibration remains a central problem in turning operations. On a giant lathe, this becomes magnified. A workpiece over 100 tons behaves less like a rigid object and more like a dynamic system. It flexes, it resonates. Under certain conditions, the cutting tool and the workpiece can enter a feedback loop. The tool cuts, the material responds, the vibration alters the next cut, and the cycle repeats. Within seconds, a smooth operation can turn into a destructive one. Surface finish degrades. Tool wear accelerates. In extreme cases, the process must be stopped entirely. This is not a rare anomaly. It is a known studied phenomenon. And yet, in simplified narratives, machining is often presented as a stable, repeatable act, as if once the machine is built, precision simply follows. Another omission appears in how labor is described. The common story suggests that machines reduced the need for human skill. Automation replaces effort. Mechanization simplifies work. But historical records of large-scale machining suggest something more nuanced. The skill did not disappear. It shifted. Operating a giant lathe was not a passive task. It required continuous decision-making, adjusting feed rates manually, compensating for thermal expansion, listening for irregularities in cutting sound. In some cases, machinists would intentionally alter parameters mid-process, based not on instrument readings, but on experience. This introduces a contradiction. If machines were supposed to standardize production, why did outcomes still depend so heavily on individual judgment? There is also a tendency to exaggerate the speed of transformation. The narrative often implies that once large machines were introduced, industries rapidly adapted, efficiency increased, systems stabilized. But archival data suggests a slower, uneven process. Factories did not instantly become optimized environments. Machines required calibration. Foundations settled over time. Alignment issues emerged after installation. Some facilities reported months or even years before achieving consistent performance. During that period, output was inconsistent. Scrap rates were higher. Adjustments were ongoing. This transitional instability is rarely emphasized. Instead, the timeline is compressed, from invention to success, as if the intermediate phase did not exist. Another simplification appears in how risk is framed. When risk is mentioned at all, it is often treated as incidental, an unavoidable but minor aspect of industrial work. But when you examine incident logs, a different picture emerges. The scale of these machines changes the nature of risk. On a small lathe, an error may damage a part. On a giant lathe, an error can involve massive kinetic energy. A rotating component weighing over 100 tons does not stop quickly. Even at low rotational speeds, the momentum is significant. If a fixture fails, the consequences escalate rapidly. This is not just more of the same risk. It is a different category. And yet, the language used in many historical summaries does not reflect that shift. it remains general, non-specific, almost interchangeable with descriptions of smaller machines, which creates a kind of distortion, not through false information, but through omission of scale. Then there is the idea of precision itself. The narrative often equates larger machines with higher precision, but in practice, scale introduces new sources of error, thermal gradients across large components, deflection under weight, toolpath deviations over long distances. Maintaining precision at this scale is not simply an extension of small-scale machining. It is a fundamentally different challenge, and one that required ongoing adaptation, not a one-time solution. So when the story presents giant lathes as the natural endpoint of technological refinement, it simplifies a process that was, in reality, still evolving, still uncertain, still dependent on conditions that could not always be fully controlled. None of this means the machines were ineffective. They worked. They enabled things that were previously impossible. But the way their history is often told removes the friction, the instability, the dependence on human interpretation, the uneven path between introduction and reliability. What remains is a cleaner version, easier to explain, easier to teach, and easier to fit into a broader narrative of progress. But when you compare that version to the detailed records left by engineers, machinists, and factory logs, a gap becomes visible, not a contradiction, but a compression, a reduction of complexity into a smoother story. And once that gap is noticed, another question begins to take shape. If the history of such a physically demanding, technically unstable process can be presented in such a simplified way, then what determined which details were emphasized and which ones were quietly left out? By the time giant lathes became central to heavy industry, they were no longer just machines. They were symbols, not only of capability, but of identity. A factory that housed a vertical lathe capable of turning a 120-ton ring was not simply a production site. It was a statement about what that company could do, about what that nation could build, about where it stood in the industrial world. And this is where the narrative begins to take on another function. Because the story of the machine was never told in isolation, it was told alongside the story of progress itself. In the late 19th and early 20th centuries, industrialization was not just an economic process. It was a political and cultural project. Nations measured themselves by output, by infrastructure, by the scale of their engineering works, steel production, rail networks, shipbuilding capacity. And at the center of all of this were machines capable of shaping massive components with precision. The giant lathe fit perfectly into this narrative. It was visible, impressive, easy to photograph, easy to display. A massive steel cylinder rotating slowly in a workshop is a clear, undeniable image of power and control, which made it useful, not in a manipulative sense, but in a representational one. Governments could point to such machines as evidence of modernization. Companies could showcase them as proof of technical superiority. Exhibitions and industrial fairs often highlighted large machine tools. Visitors would see scale, precision, order. They would not see the hours of setup required before each operation, the trial cuts, the adjustments, the failures that preceded a successful pass. Because those elements are not visually compelling, they do not translate easily into a symbol, and narratives tend to favor what can be seen and understood quickly. There is also an economic dimension. Large-scale machinery required enormous investment. Foundations alone could take weeks to prepare. Concrete bases several meters thick, designed to dampen vibration from rotating masses. Overhead cranes rated for 200 tons or more. Specialized transport systems to bring raw components into position. These were not small decisions. They represented long-term commitments. And once those investments were made, there was an incentive to frame them as not just necessary, but inevitable, as part of a forward-moving trajectory. Because uncertainty is difficult to justify at that scale, but progress is easier to defend. If a machine is seen as the next logical step, then the cost becomes part of a larger story, a story that leads somewhere. Even if, in practice, the path was less direct, there is also something more subtle, a psychological preference for coherence. Complex processes are difficult to communicate. A machining operation that depends on thermal behavior, material variability, operator intuition, and environmental conditions does not compress easily into a simple explanation. But a linear story does. Machines improved, output increased, society advanced. This structure is familiar. It fits into education systems. It aligns with how history is often organized, as a sequence of developments, each building on the last. So over time, the narrative stabilizes, not because alternative details are hidden, but because they are harder to integrate. Technical documents remain detailed. Engineering journals continue to describe complexity, but the broader story selects. It keeps what is clear, what is demonstrable, what reinforces the idea of progress, and gradually, other elements become secondary, less emphasized, less repeated, until they begin to feel peripheral, even if they were central to the actual operation of the machine. This does not require coordination. It does not require intent. It is an outcome of how information moves between contexts, from workshop to report to summary to textbook to public understanding. At each step, details are filtered, not necessarily removed, but reduced, simplified, reframed. And in that process, the giant lathe becomes something slightly different. Not just a machine that required constant adjustment, interpretation, and adaptation, but a symbol of controlled power, of precision achieved at scale, of industry functioning as a stable system. Which brings us back to the earlier tension. Because none of this is false. The machine did enable new capabilities. It did contribute to large-scale engineering. It did support industries that define modern infrastructure. But the way its story is told emphasizes certainty over variability, outcome over process, stability over adjustment, and that emphasis serves multiple purposes. It supports economic justification. It reinforces national identity. It simplifies education. It creates a coherent image of technological progress, all without needing to exclude the underlying complexity entirely, only to move it out of focus. And once that is understood, another question naturally follows. If the narrative of such a physically demanding, condition-dependent machine became more stable and simplified over time, then what happens when we return to the original records and read them without that filter? If you move away from summaries and go back to the original documents, the tone changes almost immediately. Not dramatic, not emotional, but noticeably different. Engineering logs do not describe progress. They describe conditions. A machining report from a heavy industry workshop might begin with something simple. Workpiece, forged steel rotor, estimated mass 98 tons. Ambient temperature, 28 degrees Celsius. Initial run showed minor vibration at 12 revolutions per minute. Nothing in that language suggests a grand narrative. It is specific, measured, focused on what is happening, not what it represents. And as these records continue, a pattern begins to emerge. Operations are rarely described as linear. They are described as sequences of adjustments. Feed rate reduced after onset of chatter. Tool replaced after edge degradation observed. Dimensional variance detected during mid-process measurement. In some cases, a single component required multiple passes across several days, not because the machine lacked power, but because the material did not behave consistently. Large steel forgings contain internal variations, residual stresses, microscopic differences in structure. When a cutting tool engages with that material, the response can change, even if external parameters remain constant. This is not speculation. It is recorded repeatedly, which suggests that machining at this scale was not simply a matter of applying force with precision, but of responding to a material that was not entirely predictable. There are also notes on thermal behavior, not in abstract terms, but in operational constraints. Machining paused to allow temperature stabilization. Measurement postponed due to heat expansion. Final cut adjusted after cooling period. These entries appear frequently, which indicates that temperature was not a minor factor, but a constant consideration. A steel component of that size can retain heat for hours, sometimes longer, which means that measurement taken immediately after cutting may not reflect the final dimensions, so precision becomes conditional, dependent on when the measurement is taken, not just how it is taken. Another set of documents focuses on machine setup. Before any cutting begins, Alignment must be verified, not once, but repeatedly. A large workpiece must be centered within extremely tight tolerances. Even a slight imbalance can introduce vibration during rotation. And at this scale, vibration is not just a quality issue, it is a structural one. Some reports describe hours spent on alignment alone, using dial indicators, manual adjustments, incremental corrections, all before the first cut is made, which contrasts with the simplified image of machining as a continuous, uninterrupted process. In reality, a significant portion of time is spent preparing for a cut that may last only a few minutes. There are also references to operator judgment, not in a dramatic way, but embedded in routine notes. Cut adjusted based on observed sound variation. Operator reduced depth of cut due to perceived instability. Feed modified during pass. These are small decisions, but they appear consistently, which suggests that the machine was not operating independently. It required interpretation, continuous input, and awareness of factors that were not always captured by instruments. Then there are incident reports. They are usually brief, direct, without elaboration. Operation halted due to tool fracture. Unexpected movement detected during rotation. Fixture integrity compromised. The language remains neutral, but the implications are not. At this scale, a tool fracture is not just a broken edge. It can involve fragments moving at high velocity. A compromised fixture does not simply loosen. It can affect the stability of a rotating mass measured in tens of tons. And yet, these events are recorded in the same tone as routine adjustments, which creates an unusual effect. The documents contain evidence of instability, risk, and constant correction, but they do not frame it as exceptional. It is treated as part of the process, expected, managed, integrated, and this may be one of the most revealing aspects, because it suggests that the complexity was never hidden. It was documented, in detail. Across logs, reports, and technical notes, these data were always available. The variability, the adjustments, the interruptions, the dependence on timing, temperature, and human judgment, all of it was recorded. What did not happen, at least not consistently, was the integration of these details into the broader narrative. They remained in their original context, inside workshops, inside technical archives, inside engineering discussions, while the public-facing version of the story moved in a different direction, more linear, more stable, more certain. So what the documents suggest is not a different history, but a more detailed one, a version where precision is conditional, where control is continuous, not absolute, where outcomes depend on a series of small, ongoing decisions, rather than a single, perfectly executed process. And once that version becomes visible, it changes the way the machine itself is understood, not as a symbol of complete control, but as part of a system that required constant negotiation with physical reality. Which leaves one final question. If this level of detail was always present, always recorded, then what happens when we step back from the narrative entirely and look at what remains without it? If the narrative is set aside, what remains is not a different machine. The same structure is still there, the same mass, the same rotation, the same cutting tool advancing slowly across the surface of steel. A giant lathe turning a 100-ton workpiece does not become less real just because the story around it changes, but the meaning attached to it begins to shift. Without the narrative of smooth, continuous progress, the process appears less linear, more conditional, more dependent on factors that do not align neatly into a single direction. The machine is still powerful, but not absolute. It does not impose order on material without resistance. It negotiates with it, through force, through heat, through time. Each cut is not simply an execution, but an interaction between tool and material, between intention and response, between design and reality. And that interaction is not always predictable, not always stable. Even in controlled environments, variability remains. A slight change in temperature, a subtle variation in material structure, a difference in tool wear, small factors. But at this scale, they accumulate. They influence outcomes. They require adjustment. So what remains is a process that is less about certainty and more about management of uncertainty. Not chaos, but not complete control either. something in between. There is also the human presence, not removed, not replaced, but embedded in the process. The operator is not just initiating the machine, they are observing it, listening, responding, intervening when necessary, not because the system is failing, but because it is never entirely self-sufficient. And this presence is continuous, not an exception, not a backup, but part of the operation itself, which changes another assumption, that machines gradually removed human involvement. In this case, they redefined it, shifted it, required a different kind of attention, a different form of expertise, less visible, but no less essential. And then there is the environment. The workshop is not just a background, it is part of the system. Temperature affects dimensions. Foundation stability affects vibration. Airflow can influence cooling behavior. The machine does not operate independently of its surroundings. It exists within them, responds to them, which means the idea of a fully isolated, perfectly controlled process becomes harder to maintain. What remains instead is a network. Machine, material, operator, environment, all interacting, all influencing the final result, and none of them entirely fixed. So the image changes, not dramatically, but subtly, from a machine executing precise instructions to a system continuously adapting to conditions, from a symbol of complete control to an example of managed complexity. And this does not diminish what the machine achieved. If anything, it makes it more difficult, more dependent on coordination, more sensitive to variation, which raises a final uncertainty, not about the machine itself, but about how its story has been understood. Because if, for so long, we accepted a version of technological history that appears orderly, stable, and linear, then it becomes possible that what we were accepting was not the full structure, but a simplified outline, one that made the process easier to communicate, easier to remember, easier to believe. And if that is the case, then the question extends beyond this one machine. If for so long we accepted such an orderly story of technology, how many other histories are we still repeating simply because they fit better into the narrative of progress?